Hello, I'm Jeffrey Steiner, a graduate student at the University of Connecticut, and in this video I will be discussing the modeling of the interior air environment within our modular coupled virtual testbed habitat. The modular coupled virtual testbed, as shown in this overview diagram, is comprised of a number of interacting subsystems, including the interior environment. The interior environment is necessary for the calculation of the distribution of air pressure and air temperature within the habitat. It interacts with the structural subsystem, the internal communication network, the power system, and the ECLIS, each of which provide inputs and outputs that affect change upon the system. The interior environment model utilizes a zonal model approach, in which 112 finite volume zones are used to divide the interior airspace and determine the distribution of pressure and temperature. The pressure change is determined using changes in mass in the system, which therefore affect the zonal density of each zone. The pressure decrease in this model is governed by power law of flow. The air temperature model utilizes that same zonal model approach, but instead considers the total energy to calculate the temperature distribution within the interior airspace. For the interaction between individual zones, as well as between zones and any sources or sinks that might be in the habitat, convective heat transfer is considered. Conductive heat transfer is also considered, but only in wall-adjacent zones or zones that are directly in contact with the structural wall. The pressure model receives input from the pressure control system, which is within the ECLIS subsystem. The pressure control system moderates the mass of the air within the interior habitat based on measurements taken at fixed sensor locations. The pressure control system is capable of adding mass, for example, to reach a pressure set point as shown here, or to discharge mass from the system to reduce the internal pressure if necessary. The temperature model is affected by both the structural thermal model and the ECLIS subsystem. The structural thermal model influences the temperature distribution within the interior airspace by providing the wall temperature of the internal surface of the structural wall. The ECLIS subsystem moderates the thermal energy within the system, providing heating or cooling as necessary. Both the pressure and the temperature model are dependent on interactions with the power subsystem, as the power subsystem provides power to both the pressure and temperature sensors within the interior environment. The capabilities of the interior environment model are best displayed using an impact damage scenario, such as that of case 4 of the validation cases used by the team to determine if the models were working properly in tandem. In this damage scenario, an impact event occurs at 20 seconds into the simulation, at which point the protective layer and the structural wall are both fully penetrated, creating a hole that exposes the interior environment to the exterior environment. At this point, it can be expected that the internal temperature would progress rapidly towards that of the exterior environment, and that the internal pressure would drop rapidly. Both of these changes can be seen in the plot shown here, where at the 20-second mark, the internal temperature and the pressure both begin to drop. Once these drops occur, the ECLIS subsystem kicks in and attempts to stabilize the system long enough so that a repair action can be taken. This is just one scenario that highlights the central role that the interior environment model plays in displaying the resiliency of the habitat system. Thank you.